Hello everyone, my name is Harshit. So today we are going to look at a solution created by LinkedIn, which aims at solving customer service question answering, and they have solved this using racks with knowledge graphs. So yeah, let's go home. Okay, so the problem statement is pretty simple. Given a large set of issue tickets at LinkedIn, when a user wants to question or query these systems, um, the solution should return the best, most accurate response. So the questions could be something like, help me reproduce the issue where user saw CSV upload error in updating user email. So the solution system should actually go and find out those tickets and extract the particular intent that the user is trying to fetch from the system. For example, let's say user wants to reproduce the issue, so there must be some given steps in some of the tickets. So the solution should extract that particular information and give out as a response to the user along with the ticket ID. The problem statement, so the second problem with these kind of systems is, when we talk about ticketing systems wherein we have large number of issues, it's not necessary that they are mutually exclusive. So multiple tickets are connected to each other in some or the other way. For example, one ticket could be a copy of another ticket, or one ticket could be a very relatable similar ticket as to some other ticket, or there could be some preceding tickets, some extensions to some tickets, there could be some additional information present in some related tickets, etc. And there are a lot of intra-ticket relationships also. So for example, one ticket can have, let's say, comments, descriptions, summary, steps to reproduce, priority, etc, etc. So a lot of information, meta information, which also needs to be connected in some way inside the ticket as well. So let's see how they solved it. So when I talk about the solution, it's pretty brief. So what they have done is, they have solved it using knowledge graphs, which solves the relationship part of the tickets, and this helps them retaining the intra-issue structures and also the inter-issue relationships. So given any query by the user, they first of all parse that particular query and retrieve all the most relatable subgraphs from the knowledge graph, and then make use of LLM to feed in these subgraphs as context along with the original query and generate some really good responses. Okay, so let's first discuss how would a conventional approach would look like using RAGs. So let's say we are trying to build a solution, very simple solution, RAGs with LLMs. How would that look like? So we can consider all the issue tickets as some plain text, containing all the textual information. There could be some image information as well, so let's ignore that thing for this particular explanation. So let's suppose everything is textual. Entire text information can be actually segmented into smaller chunks. Obviously the chunking that we do in racks, and obviously this chunking can be of many different types. You can assume any chunking methodology. The chunks have to have to accommodate the constraints length of the contexts, obviously. Now each chunk has to be converted into a embedding vector. Let's say we are using E5 for finding the embedding vectors for each chunk. Now given any query, there are two steps to follow. First is find out the most relevant chunks which are very similar to my query, right? And extract out those chunks and give it to the LLM as an additional information in the context for LLM along with the original query to generate the response. So this is how a simple RAG system would work for such a problem. I have depicted it here in terms of a diagram also. Let's say there is any ticket which is just a bunch of text. We are bifurcating the ticket into multiple chunks and those chunks are converted to vectors. So given any query by the user, this query will first be converted into an embedding vector itself. Now this embedding vector is matched with entire vector space in the vector database, and let's say we found out that vector 2 and vector 4 are most similar to this query. Now those are retrieved from this particular vector database, and yes, these vectors could be from multiple different tickets also, right? Now these are augmented into the LLM as an additional information, and yes, the response is generated. This is how a conventional RAG would look like. Now, what are the limitations of such solution given this particular use case? So obviously, the first thought is there is a lot of connectivity inside tickets. So tickets cannot be considered as just plain text, because let's say a particular ticket was connected to particular another ticket, and this connection went out for, let's say, 2-3 steps, and in the fourth ticket actually the solution was present for the ticket A. Now this is something, this relationship is really important to find out or fetch the best results of the user query, right? And obviously chunking methodology would lose out on any such relationships. Second problem is chunking also would lead out to loss of important piece of information within the ticket itself. So let's say we chunked out the ticket and there are n number of chunks, and the first chunk matches the user query perfectly, but the last chunk doesn't match it and doesn't become a part of the context of LLM, and actually the solution was present in the last chunk. Now this brings out the problem that chunking led to loss of that particular information, which was the crucial bit, right? How they actually solve this? They have made use of, again, the knowledge graph. So knowledge graph helps to maintain the relationship, inter-ticket relationship, you can say, wherein we know that now ticket A is connected to ticket B, ticket C, then ticket E, and so on and so forth. So, and these inter-issue tickets could be either explicitly mentioned in the tickets, or the authors have actually extracted out implicit matching tickets as well, using embedding based matchings. The second thing, they have solved it using intra-issue tree, wherein they are preserving some meta information and making out some blocks and nodes to actually bifurcate those pieces separately, so that any particular piece of information needed could be just passed by traversing the graph itself. So let's look out at an example to understand things better. So let's say let's see how this particular query can be solved using the entire approach that we discussed. So look at these legends first. Now these signs represent the tickets. So there are step numbers also mentioned, so we'll follow by the step numbers, and these blocks are the graph nodes. Okay, and anything mentioned with this particular sign is actually solved by an LLM. Okay, so we go to step 1, which is intra-ticket tree parsing. Herein the authors show that, let's say we are talking about this particular ticket 22970. This ticket is of an issue which is CSV upload error updating user email. Now there could be multiple things associated with this ticket. For example, the summary of the ticket, the description of the ticket, the fields that it has, for example, the priority, the root cause, etc., etc., comments, descriptions, steps to reproduce. So every logical connection is actually drawn out in this particular intra-tree representation. The second step is the inter-ticket connections. As I said, there could be implicit and explicit connections. Explicit ones are very simple, but implicit ones are calculated using any simple EBR. So let's say this is the inter-ticket connections, and this ticket is then connected to all the matching tickets, like in this way, making a complete graph of this system connecting these particular nodes. Do note that these blocks are the graph nodes. which takes us to the third step, which is all the graph nodes are converted to text embeddings and stored in the vector database. Okay. Let's go to the fourth point. So let's say a user queries and writes out how to reproduce the issue where user saw CSV upload error in updating user email and has major priority that was caused by data issue. So the first step is extracting out some entities by the LLM, and they have preset these things. So let's say they are trying to find out the summary using LLM. The summary of this particular query comes out in this particular block. The priority they are finding using LLM again. So priority is major. The root cause again by LLM, which is data issue. And the intent, what does the user want from the response. So the user wants steps to reproduce. So all these piece of information are actually extracted using LLM only. Now these green bits are important to filter out to even granular things and find out tickets which are even better. So improves the search basically and pinpoints to the good tickets. And when we say we want to match to certain type of this particular issue that the user has asked, then again embedding based retrieval is done. So this particular piece of information would be matched with all the nodes present in the graph. So let's say this particular summary matched with this particular node information. Now we know that this ticket is in action. All the information connected to this particular node can be easily traversed to a graph traversal, and we know the intent of the user, which was to reproduce the this particular issue. So we can extract out this particular information from the graph and any other information that could be present in some interconnected graphs as well, interconnected tickets as well. So this makes out really useful to extract out only the relevant information and complete information rather than just finding out chunks which could be disconnected, completely disconnected, right? In the sixth step we can see the answer was generated, although it doesn't exactly match the response, but a very good answer related to this particular query. Now let's see how they evaluated this particular piece. So they created their own golden data set which consisted of queries, support tickets and the solutions, and the baseline model they used was the one we discussed, conventional text-based EBR. They have used the same LLM for both the methods, which is GPT-4, and the same embedding model as well for both the methods. And the two broad metrics they are using are retrieval based metrics and the question and answer response metrics. So in retrieval based metrics, what they mean by this is you can find n number of tickets answering your query. So what's the rank of the best answer? So for example, the response gave out 10 tickets to you and the best response was on the third ticket. As we have the golden data set, we know which answer is the best from which ticket. So here we are trying to evaluate the rank of the given responses, and three simple metrics they use are MRR, recall at k and NDCG at k. And when it comes to comparing the textual response, they have used blue score, row score and meteor score. And when we look at the metrics objectively, the improvement is huge when compared to baseline. You can see recall at 3 is exactly 1, which means it's 100% sure that they are getting the response within 3 tickets itself. There's significant improvement in MRR and NDCG as well. When you look at blue score, meteor score and rogue score, again the improvements are huge. So this clearly indicates that such use cases or such problem statements are pretty much suitable with knowledge graphs with RAG rather than conventional RAGs. So yeah, really good solution by LinkedIn. So this was it, and let's catch up in the next videos. Thank you.